Again, welcome to Core Volunteer Training. We're in luck tonight. We have our very own resident climate scientist. And what I'd love to do is just start off by having a chance to introduce Dr. Kirtland Turner. She's given us permission to call her Sandy. So here's a little bit more about Sandy. Sandy's been an assistant professor of paleoclimate and paleoceanography in the Department of Earth Sciences at the University of California, Riverside since 2015. Previously, she was a National Science Foundation International Research Fellow based at the University of Bristol in the UK, and earned her doctorate from Scripps, along with our very own legislative director, Danny, back in 2012. Her research uses a combination of geochemical data and climate modeling to understand carbon cycle and climate feedbacks on a warmer climate. She reconstructs episodes of climate warming in Earth's past and evaluates what these ancient global warming analogs can tell us about the future Earth. She's also been involved with CCL since 2008 and is now on the board of our sister nonprofit for Citizens Climate Education. Welcome, Sandy. We're honored to have you. And before I turn it over to you, I'll just go over a couple of quick learning goals for tonight's webinar for Core Volunteer Training, and they include the following. Hopefully after tonight, volunteers will be able to understand the natural carbon cycle and especially emphasize the basic concepts behind climate change, including carbon dioxide trapping heat, the concentration of carbon dioxide rising, and human contributions driving this rise. The next also high priority learning goal is describing the importance behind the scientific method and peer review process, as well as implementing best practices and communicating this research that we're going to be talking about with other community members in the field. I know that that was a couple of attendees' earlier questions that they submitted before the webinar. And then lastly, in our action section tonight, we're going to find out more information about how to and where to connect with climate scientists local to your own group. So with that, real quick, tonight's agenda looks like the following. First, we're going to talk about more behind the carbon cycle. Then we're going to have a chance to discuss the anthropogenic links to that, as well as the scientific method and the importance of peer review. We're going to talk a little bit more about what we can do about it, and then really have some Q&A, which will probably actually be interspersed a little bit earlier than that. And then we'll land on a moment of inspiration, learning from the past science, and then get involved with our partner action plans. And I'll pass it over to you, Sandy.
Great. All right, so I thought I'd start with just a little bit of my personal story about why I'm motivated about climate change so everyone can get a sense of where I'm coming from. The picture on your screen right now is I was lucky enough to get to go down to Antarctica a few years ago now, back in 2009, and was really just awestruck by the beauty of the continent and how special of a location this is on the planet. There's just truly nothing like it. And I think it's important to remember how this place that seems so distant from us is actually someplace that will begin to become much more relevant for all of us on a daily basis if it begins to melt. We talk about sea level rise, and we'll get to the rates of sea level rise that we've seen over the last decade later tonight. But just as a take-home message, remember, if the Antarctic continent melts, we're talking about 60 meters of sea level rise equivalent that's locked up in that. That's enough to change really the shape of every continent on Earth today. So some place that's really beautiful and I would like to preserve for its own sake, but also has the ability to really hit us at home where we live. So just a little bit of background. And unfortunately, it's not just the basics of climate change and the whole globe's warming that we have to be concerned with if we're trying to ask whether or not Antarctica will persist for the next generations to come. Unfortunately, if we look at the high latitudes, the Arctic region, especially opposite from Antarctica, but again at the poles, is warming faster than anywhere else on Earth. And so that's something that I really want to also present as a take-home message tonight, the fact that warming is variable depending on where you are at the planet, how fast we expect the world to warm over the next century, how severe that warming will be. And the Arctic or the high latitudes are hit really, really hard. So we've already seen massive disappearance of Arctic sea ice, for instance. We see this melting of land-based ice, like down in Antarctica, but also in Greenland in the Northern Hemisphere, that's contributing to sea level rise. And we even see melting of permafrost, so frozen soils in the high latitude tundra that are actually releasing additional greenhouse gases, things like methane and CO2, to the atmosphere and exacerbating the problem. So this is just some of the background of what I'm really concerned about moving forward, protecting some of these valuable places, both for their own sake and also so we prevent some of the most severe consequences to society. Okay, so really now I'm going to go into some of the basics, what we know about climate change. And the way that I've hopefully broken this down a little bit is to go back over some core facts that I think most people on this call have probably heard before, but then add maybe a little bit of nuance and also describe how I personally have decided over the years to address questions that I hear a lot. So I do a lot of talks on climate change. I teach climate change to undergraduate students, and there are certain things that just come up over and over again. And so interspersed in these slides, I have some slides that are really just one or two sentences on the slide of literally the language I think that's most effective to use, or that in my experience has been effective to use in answering some key climate change questions. So let's kick it off. All right. Oh, let's go back a second. So the most fundamental and first place to start is always to just say these foundations of our modern society, the type of energy that we use are hydrocarbons, right? That's coal, oil, and natural gas. And when we burn hydrocarbons, they produce carbon dioxide as a byproduct. That's just a really basic but critical fact to know. All right. And we're burning lots of these things, right? So this graph comes from the Intergovernmental Panel on Climate Change. The most recent report was AR5 in 2013, although we have a new report that's coming out again soon. And this is from a document that hopefully everyone should download and read. It's the Working Group 1 Summary for Policymakers. So this is the summary of the physical science basis behind climate change. And this was kind of their state of, as of 2013, their sum of all of the anthropogenic greenhouse gases that human activity has emitted over the last few decades. And this is broken down by colors into different types of greenhouse gases. But you'll notice that the largest one of those, this orange bit, is carbon dioxide gases, right? So this bit above in the slightly darker orange is sort of like an equivalent CO2 from land use change. So when we convert forests and things like that. So not directly burning it, but effectively adding CO2 to the atmosphere anyway. And so you can see that really dominates the picture of greenhouse gases. We're releasing things like methane, which is this light blue, CH4, and nitrous oxide, which is the turquoise color above. And these fluorine gases are much more minor components. And the critical point that I've got on the side here is these are sources of carbon dioxide that are not accounted for by any natural ability of the planet to take up that CO2. So that's like an extra addition that is adding to the concentration of CO2 in the atmosphere. All right, so what does that do? Well, of course, on our planet, we're lucky enough to have a natural greenhouse effect. Right? So that is the ability of our atmosphere to trap heat. And that's really critical. Without that, our planet would not be habitable, right? So we would be significantly cooler. We'd actually have an average planetary temperature that was negative 18 degrees Celsius. It's below freezing. So we need a greenhouse effect. But when we increase these greenhouse gases, carbon dioxide being this primary one that we'll get to in a moment, as it is today, 43% above the level that it was before we started industrial activity, we enhance the greenhouse effect. And if we get into some of the details of why the planet is the temperature it is, effectively, the planet's temperature is set by this need that the planet has to balance with outgoing energy, the amount of energy that it gets from the sun. And so if we add these heat-trapping gases to the planet's atmosphere, the temperature of the Earth has to rise in response so that we stay in energy balance and we're giving off enough energy to space to balance the amount that we get from the sun. All right, so that's an enhancement to the greenhouse effect. So just again, some of those fundamental points. A greenhouse gas is really any gas that absorbs and gives off energy in the thermal infrared range. So think of heat, right? And any gas will do this if it's made of a molecule that has 3 or more atoms. That basically affects its ability to vibrate. So if we think about what our atmosphere is predominantly composed of, that's nitrogen and then oxygen. Those are our 2 most common gases in the atmosphere. But we never talk about them when we talk about climate change or global warming, because these gases just have 2 molecules, and so they can't vibrate in a way that traps heat energy. So they're kind of irrelevant for the question of what's going on with the heat trapping effect of our atmosphere. So CO2 is particularly effective because it absorbs in this window where water vapor is less efficient. So you might have heard someone say before, CO2 doesn't matter because water vapor is the most important greenhouse gas. And even though that's true, there's 2 things that we have to say are caveats to that point. The first is, again, that CO2 happens to be effective at absorbing heat energy where water vapor isn't. And the second fact is that water vapor itself is controlled in its atmospheric concentration by the temperature of the planet, right? So it can vary spatially on the planet anywhere from being 0%, in a desert where there's no water vapor, to up to about 4% of the atmosphere in really humid areas. But if you didn't change the concentration of these other greenhouse gases, water vapor wouldn't change. So it's responding to the temperature rather than driving it. So that's a really kind of key distinction to make. All right, so moving on. So just a nice summary way of kind of pointing out how effective carbon dioxide is as a greenhouse gas is to use this term that's from the IPCC and extensive in climate literature, which is the global warming potential. And so we can say that carbon dioxide has a very high global warming potential. And that's basically saying that it's very efficient at absorbing energy right in those wavelengths of energy where Earth is releasing heat back into space. And because of that aspect of that molecule, we're able to trap heat efficiently. And then secondarily, because CO2 stays in the atmosphere for a very long time, it can continue to be effective as a greenhouse gas for a very long time, compared to something like methane, which cycles really rapidly throughout the atmosphere and won't stay in the atmosphere for more than decades. All right, so all of that summary, the fact that we're adding this CO2 by burning fossil fuels has a consequence, which is that Earth's temperature is warmed. And so this is just a summary graph that is pretty typical that we report temperature change relative to an average. So this is an increase in temperature compared to the average of those decades from 1961 to 1990. And so you can see this consistent rise in temperature. It's not completely straight, right? We have variability year to year. There are lots of other things that control the exact temperature of a given year, but the trend is clearly upwards over the last century. And as we'll see, we can actually start to reconstruct this trend further back in the past as well. And we've warmed by about 1 degree. All right, so if you want to, sometimes I think trends and graphs like that don't really capture people's attention. So this was actually something I put together last year. You can always go to the NASA Goddard Institute webpage, which is where this figure comes from, because they're constantly releasing the most up-to-date estimates of the global temperature. But I like to say last year in October, which is when I grabbed this image, was the warmest October in 100, or was the second warmest October, sorry, in 136 years of modern record keeping, with 2015 being the warmest. And I think sometimes when you say things like that, rather than trying to show a trend line and talk about 1 degree or something like that, this kind of fact really grabs people's attention. And this is a major effort to take the pulse or the temperature of the globe in any given year. And when sometimes maybe people are skeptical about how we know this, you can point out the massive amount of data that are behind these measurements. So here you can see over 6,000 different worldwide temperature stations or weather stations. The data from all of those are assembled in order to get an estimate of how much the planet has warmed. And the other thing I wanted to point out about this image is, again, you can see that the warming isn't the same everywhere. So look at that big dark red blob right over the top of the northern latitudes. That's this amplified warming that we see in the high latitude as a consequence of what we call polar amplification. And also notice that the US is not doing so great in terms of the relative amount of warming either, right? So this is a sort of a summary slide. The point to take home is that we're forcing the climate system by raising atmospheric CO2 concentrations. The response to that forcing is an increase in surface temperatures, right? So we've got the famous Keeling curve. We've only been measuring carbon dioxide in the atmosphere from the late 1950s on. And you can see this rise year after year till today. We're actually off the scale, of course. We are above 400 parts per million CO2 in the atmosphere. And the observed temperature response, again, you can see that it's spatially variable. On average, we're at greater than 1 degree Celsius warming already since the start of the Industrial Revolution. But we can reconstruct things further back in time. And I think that that's an important point to emphasize to people that really might wonder, is this just a natural cycle? We have amazing ability now to take measurements that go back into times before humans were around actually measuring these things. And in particular, we can use the ice core record to actually reconstruct how much of these different greenhouse gases were in the atmosphere before we began the ability to generate the Keeling curve. So if you look at this graph, we've got carbon dioxide concentrations in the green line at the top. And this is now going from the very, more modern time. You can see that sharp increase on the right-hand side of the graph, but we're moving back 11,000 years ago. So this is now getting into a much longer history. You can also see methane concentrations in the middle and nitrous oxide. Those are those other two less important greenhouse gases below. And what you can see is that the values that are occurring today, and remember, again, if we concentrate on just CO2 here, 400 parts per million is off this axis, are truly exceptional. So in the last 11,000 years, we were never above 280 parts per million of CO2. And I'd just like to point out, that last 11,000 years encompasses all of the modern civilizations that we learn about at school, right? So the ancient Egyptians, the Mesopotamians, all of the establishment of modern civilization happened when CO2 was below 280 parts per million. All right. Okay, so sometimes you might hear about something called the hockey stick curve, which is now moving back into saying what were temperatures doing over this longer interval of time. And the hockey stick refers to the fact that if you look at just modern temperature change over the last few decades and you compare it to these reconstructions, it looked like a relatively flat line with this curve just in the last few decades. So it looked like a hockey stick. And this is a kind of a rethink of the hockey stick that was presented by the National Academy of Sciences in 2006. And the point is that we have to use a variety of what we call proxy methods for estimating temperatures before we had thermometers around. And there are a variety of ways to do that. So all of the different colored lines on this graph show for the last 1,000 years, all of the different ways we can reconstruct temperature. So that's everything from looking at tree rings to reconstructing aspects of how far glaciers have extended past their modern lines, to even looking at temperature changes when we drill down into the ground and look at temperatures in the deep subsurface. And either way, the point is, again, modern warming stands out. So we kind of know that along with lower CO2 levels, the planet was cooler until we started pumping carbon dioxide into the atmosphere. All right, next one. So another question I get sometimes is, how do we know actually that humans account for the rise in CO2? Now, aside from the fact that, we know that we've been burning fossil fuels and that should generate CO2, we can actually detect the chemical fingerprint of the fact that this CO2 comes from human activity. So on the top here, the green line is, this plot is the carbon dioxide concentration. You can ignore the blue lines, that's oxygen, we won't talk about that. But on the bottom of these two plots, the green line is showing basically, all we need to say here is it's a chemical fingerprint of the carbon dioxide gas that's in the atmosphere. And you'll notice that this has a really clear trend to it over the last few decades as well. It's this drop in this value. And this value is basically our fingerprint that says the CO2 that's been going into the atmosphere is coming from burning fossil fuels, because they have this very unique chemical fingerprint. This is exactly the opposite of what we would see if the CO2 that was adding to the atmospheric concentration today came from volcanoes. If that was the case, this bottom graph would be a straight line. It wouldn't have changed at all. So we actually can definitely verify where the CO2 comes from. All right, next one. So now I'd like to get into a little bit about what's feasible, because sometimes I think this is the gloom part. Hopefully we'll get to some positives in a moment. So far, if we talk in units of 1 billion tons of carbon, which is a truly massive quantity, then so far humans have emitted this top bar, 300 billion tons of carbon. And I like to use as an analogy, that's as if every person in the United States, right, was emitting something like 1,000 tons of carbon. And that's kind of the magnitude that you get, really just a massive amount. So we're releasing about 10 billion tons a year right now. That rate of carbon release is accelerated. If we continue on that trajectory, we will have easily surpassed 1,000 billion tons or gigatons by the end of this century. If we do that, we're talking about probably on the order of 5 degrees warming easily. But we could burn something like 5 times that much if we just continue to go through all of the fossil fuels that we know exist today, right? And for comparison, if we just think about that yearly rate, we're looking at emitting about 100 times as much carbon as comes from volcanic CO2 emissions every year. So we've become the massive source of carbon into the Earth system, right? So some projections, if we actually did burn all that amount versus if we start to curtail our emissions. The Intergovernmental Panel on Climate Change uses these different scenarios in order to make predictions about what temperature change will be like at the end of the century. So if we reduce all of our emissions to 0 by the year 2100, we're still looking at a warming planet, but we can keep a lot of warming down within this 2-degree range. In contrast, a business as usual scenario has us again warming by on average more than 5 degrees, with some spots of the globe warming by twice that much, particularly if we look at those high latitudes. All right, so I think at this point it's kind of key to get to the point that this is all fundamental science, right? If you go and you poll climate scientists, you won't find people that disagree with any of these basic facts that I've kind of gone over so far, right? So again, you might find a very, very few individuals, but if you look at the mass of scientists who are publishing, these are agreed on aspects of the science. A lot of the so-called skeptics are not even debating these points. They start asking questions about the exact amount of warming that we'll see by the end of the century. But the fundamentals of CO2 being a greenhouse gas, they won't get into. About how we know that it's human activities that are adding CO2 as opposed to natural processes. But how do we know that these other things that drive the climate naturally aren't causing the warming that we're observing? This was a slide that CCL already had, and I just kind of added a few more details to this. The first is the sun. A lot of people say the sun causes all of it. And again, I think the key point here is that, we actually can take a look at what the sun is doing, right? We have that ability technologically. This is satellite data of solar output since 1978, which is when we put in the first space-based instruments to measure solar output. You might notice that this doesn't look anything at all like the trend line that we've seen in temperature over the last few decades. So this is an 11-year sunspot cycle that you're seeing on this graph. It's a well-known thing. The point is that the sun has not been steadily increasing its output in any way that can account for warming of the last few decades. And actually, we can use, again, this indirect or proxy evidence to look at solar output moving back into the past as well. And we can see that before humans began adding all the CO2 to the atmosphere, temperatures did agree really well with changes in solar activity. It's just that since human activities have sort of hijacked this system, we now, of course, are looking nothing like changes in solar output. And so that's distinct from the orbital forcing of climate, which I also get questions about a lot. So this is not now how much energy the sun is actually emitting, but this is how much energy from the sun we receive based on how the planet, the Earth, is moving around the sun. And this is a really important control on climate over the very long term. So we're talking tens of thousands to hundreds of thousands of years. But again, this is something that is actually really easy, not easy, but it's something that specialists can do. We can calculate how these sort of different paths that the Earth is taking around the sun have changed through time. We can actually do this both deep into the past, around 40 million years, and about that much into the future as well. And then we can say, okay, this is how much energy from the sun we should be receiving as a function of these different changes. And of course, again, we can say that that is A, not consistent with the changes that we've seen over the last few decades, and B, these cause variations in temperature on a much longer timeline. It doesn't account for things like decadal fluctuations. And then I think, I hear this argument, well, the climate's changed before. And I like to always immediately say, you know what, that's absolutely true. You never debate that point. But the fact that the climate's changed before based on natural processes in no way means that humans aren't behind the causes of climate change today. So I like to be really upfront with talking about past examples of climate change, because we can use that in order to learn about, how the Earth responds when you change CO2, or how ecosystems respond when the climate changes. So, I already talked about ice cores. We can look at past changes in CO2 for the last 800,000 years and see how temperature has correlated with that, which gives us a lot of confidence between, or in terms of how carbon dioxide levels control the climate. And so we could see that correlation in the past. And so we should be concerned about how CO2 levels impact temperature. So that's one example. We can go even further back in time, and we can reconstruct times in Earth history when atmospheric CO2 levels were much, much higher than what we are seeing today. We're talking now millions of years into the past. I have a slide on that. I think it's the next one. And the point is that, this one, yeah. And so this is just a little graph showing atmospheric CO2 from all these different proxy measurements, now moving beyond ice cores for the last actually 65 million years. And we can reconstruct temperatures then. And the key point here is just that these are things that we can study, but we can also study how bad, some of these high temperatures or rapid warming events were actually for life on the planet at those times. So rather than say the climate's changed or we don't care, we should kind of turn that around and say, yeah, we know the climate has changed before from natural mechanisms that were still quite destructive. I mean, now imagine how bad it is when humans are doing something that is totally not natural to the climate system.
And how lucky are we to have one of the authors of this 2013 science paper here actually be on the call?
Yeah, so I like to do this for people. It's not a perfect parallel, but I think sometimes after giving a lot of the scale of the problem is so daunting, and it has a lot of scary impacts. So I like to kind of close with, human activities, when we all come together and agree that we're going to address a problem, can actually cause some remarkable things to happen. So tell the story of the ozone hole. When the ozone hole was recognized, it was like, people were really freaked out, right? I mean, ozone is this molecule that's produced by a lot of, ozone is a molecule that's very important. It's produced in the upper atmosphere when UV light reacts with the oxygen gas that's in our atmosphere. It's regularly created and destroyed, but we have this rough balance. So it's a temporary molecule, so it's slightly different than CO2. So ozone is really critical as well because it's important for protecting humans from ultraviolet light. So without ozone, we would be much more susceptible to damage from the sun's rays, much higher cancer risk. Even the photosynthesis going on in the surface ocean would be compromised without ozone. So it's a really critical element, to our atmosphere for protecting us. So get the next one. Okay, but then I forget the exact year for this, but when chlorinated fluorocarbons, or CFCs, came out, they were looked at as a sort of dream chemical because they were non-toxic, they were non-flammable, and they had all of these uses. So they were used, apologies for the typo, but they were used for refrigeration, they're a propellant for aerosol spray cans, they were in plastics, solvents for dry cleaning. So really a very sort of like a super molecule. And no one thought about this at first. It was a very lesser known side effect until scientists actually started going out and measuring some of these things. But unfortunately, when chlorinated fluorocarbons are released into the atmosphere, they can make it up into the highest parts of the atmosphere, where they break down into these chlorine atoms that just attack ozone molecules. And they split them up. And so we end up with oxygen and this chlorinated or chlorine monoxide molecule. And so they're destroying ozone levels. So that was obviously a big problem, and that just because of the details of atmospheric circulation led to this ozone hole, sort of, or low area of ozone concentration centered over the Antarctic region, sort of in the high southern latitudes. But humans sort of rallied quickly because this was a really scary thing, right? They even saw impacts pretty rapidly in people that lived much closer to the ozone hole from exposure to UV. So you can see when the ozone hole was discovered in the 1980s, and this is a graph that's showing then the concentration of these CFCs in the atmosphere. And what happened is an international group convened, and the Montreal Protocol was passed just a few years after the discovery of the ozone hole. And almost immediately, the production of these CFCs were just leveling off. So you can see that by the early 90s, within just a few years, the concentration had stopped increasing, and CFCs were being phased out entirely. And as a consequence of that decision, we've already started to see the ozone hole repairing itself. And in fact, now we can sort of project out, based on the rates that ozone forms naturally, that by the middle of this century, we should pretty much have recovered concentrations of ozone over the Antarctic continent. So the key point here is that, early on, we had a situation where the international community recognized a problem that was brought to their attention by sciences. And despite there being a lot of economic advantages to using these CFCs for all sorts of activities, we were able to ban them, and it's immediately had a really big and important impact that will improve, the health of many, many people nearby as a consequence.
Is just give a huge round of applause again to Sandy. Thank you so much for your time tonight. It's an honor to learn from a real expert like you in the field. And I'll just also emphasize this. After tonight, if you're looking for this webinar, here is, speaking of emails, how to get a hold of Sandy as well as myself. Here is the link to where to find the actual recording. We can also find those on the Learning Center. So if you go either to Core Volunteer Training here, or if you go down and click on the recording links, you'll be able to find this emphasis. And we really want to make sure that people have access to all the slides with all the resources that Sandy's really put a lot of time putting together.
And please do feel free to email me if you have any additional questions. I know that was a lot of stuff pretty quick, and I'm happy to clarify things further. Just let me know.
It's a big ask to put all of climate science into a 20-minute presentation. I think you did a stupendous job with it, and we are lucky to have the chance to learn from you. And we'll see you all next week. Thank you.
Thanks again.